Dear students, in this lecture we shall derive the time-dependent Schrödinger equation. Before that, we shall aware with the wave function, so let's start. The quantity that characterizes the waves is called wave function. It is denoted by psi. It may be a complex function. This quantity psi is assumed to have three basic properties, such as it can interfere with itself, so that it can account for the results of diffraction experiment. You can follow this experiment with more details in my previous lecture. See the link in description box. It is large in magnitude, where the particle is likely to be, and small elsewhere. It describes the complete space-time behavior of a single particle, not the statistical distribution of a number of such particles. Now we shall derive the time-dependent Schrödinger equation. If psi of xt represents the wave function that's specified in the x direction, we write psi of xt equal to a e to the power ikx minus omega t, where a is the amplitude of the wave, k equal to 2 pi by lambda, known as magnitude of the wave vector, lambda is the wavelength of the wave, and omega equal to 2 pi nu is the angular frequency and nu is the frequency of the wave. Differentiating psi with respect to x twice, we get del 2 psi del x2 equal to minus k square psi. This equation is denoted by number 1. Again differentiating psi with respect to t, we have del psi del t equal to minus I omega psi. This equation is denoted by number 2. Now we multiply equation 1 by minus h line square by 2m and we get minus h line square by 2m del 2 psi del x2 equal to h line square k square by 2m into psi equal to h line omega into psi. This equation is denoted by the number 3 because for free particle of mass m and momentum p, the energy is E equal to p square by 2m equal to h line square k square by 2m equal to h line omega. Since from the equation we have p equal to h by lambda equal to h line k, where h is the Planck's constant. Now we multiply equation 2 by minus I h line and we get minus I h line del psi del t equal to minus h line omega psi, or I h line del psi del t equal to h line omega psi. This equation is denoted by the number 4. Equating the equations 3 and 4, we get minus h line square by 2m del 2 psi del x2 equal to I h line del psi del t. This equation is denoted by the number 5. This is the one-dimensional time-dependent Schrödinger equation for free particle of mass m. If the particle is acted upon by a force derivable from a potential V of x, then the total energy is given by E equal to p square by 2m plus V of x, or h line omega equal to minus h line square by 2m del 2 del x2 plus V of x. Hence from equation 5 we have I h line del psi del t equal to minus h line square by 2m del 2 psi del x2 plus V of x psi. Similarly, the equation for the wave traveling along y and z axis respectively will be I h line del psi del t equal to minus h line square by 2m del 2 psi del y2 plus V of y psi, and I h line del psi del t equal to minus h line square by 2m del 2 psi del z2 plus V of z psi. Thus, the three-dimensional time-dependent Schrödinger wave equation will be I h line del psi del t equal to minus h line square by 2m delta square psi plus V of x y z psi, where delta square equal to del square del x square plus del square del y square plus del square del z square, known as Laplace's operator. Now we shall discuss the properties of wave function. The wave function must be well behaved, that is, single valued and continuous everywhere. If psi1x, psi2x, psi3x and so on are solutions of Schrödinger equation, then the linear combination psi of x equal to a1 psi1x plus a2 psi2x plus a3 psi3x and so on must be a solution. The wave function psi of x must approach 0 as x tends to plus minus infinity. Now we shall know about the well-behaved wave function. It must be continuous everywhere. All its partial derivatives such as del psi del x, del psi del y, del psi del z, etc. must also be continuous. It must be square integrable. This means the integral integration psi star psi d tau must exist. Since the integration psi star psi d tau is the probability density, the wave function must be single valued everywhere. The wave function must be finite everywhere. That's all.